Good morning and welcome to the first ATCO SpaceLab Speaker Series session of 2024. My name is Claire Porbay and I'm a member of ATCO's transformation team, and I'm pleased to be your moderator today. I acknowledge the Indigenous peoples that are traditional custodians of the land that we are on today. While this is a virtual platform, I'll take a moment to reflect on the meaning of place, and in doing so, recognize the various traditional, ancestral, and unceded lands on which we do our business. I do this to reaffirm my commitment and responsibility in improving relationships between nations and to improving my own understanding of local Indigenous peoples and their cultures. I'm honored to live and work in Treaty 7, the traditional territories of the Blackfoot Confederacy, Nitsitabi, comprised of Siksika, Kainai, and Piikani nations, the Tsuut'ina Nation, and the Stoney Nakoda, including the Chiniki, Bearspaw, and Goodstoney First Nations. The city of Calgary, Mohkinstsis, is also home to the Métis Nation of Alberta, Region 3. I'd also like to pay my respects to elders, past, present, and upcoming, in the communities and regions where we operate. Our speaker today joins us from the Simon Fraser University in Burnaby, British Columbia. I'd like to respectfully acknowledge the unceded traditional territories of the Coast Salish people, including the Tsleil-Waututh, Coquitlam, Squamish, and Musqueam nations, on which SFU Burnaby is located. Now, a quick comment on the lecture format before we get started. Today's lecture is a one-way video and audio format. Please ask questions by using the question icon on the right of your screen. We will open question functionality shortly after starting today's lecture. I encourage those of you who are new to today's topic to approach this time we have together with a growth mindset. We're certain that if you do, you'll walk away today having learned something new. I would now like to hand it over to my friend and colleague, Andrea Kleiber-Langen, Vice President Transformation with ATCO's Transformation Team, to introduce our speaker today.
Thank you, Claire. Thank you all for joining today. We are thrilled to have the distinguished Dr. Ljiljana Trajkovic join us, an accomplished professor with the School of Engineering Science at Simon Fraser University. Dr. Trajkovic received her PhD in electrical engineering from the University of California, Los Angeles, and her research interests include communication networks and dynamical systems. She has held several leadership positions in the Electrical and Electronics Engineers, or the IEEE organization, including president of the IEEE Circuits and Systems Society. Dr. Trajkovic serves as editor-in-chief of the IEEE Transactions on Human-Machine Systems and associate editor-in-chief of the IEEE Open Journal of Systems Engineering. She is also a fellow of the IEEE. Today, Dr. Trajkovic will discuss how we may better understand modern communication networks through the collection and statistical analysis of network data. She will share how that analysis assists in our determination of traffic loads, analyses of user behavior, and our prediction of future network traffic. One way that ATCO may leverage these insights is in how we may design a more effective threat detection system for grid networks. We are honored to welcome an expert of your caliber, Professor Trajkovic, and we eagerly anticipate the enlightening session ahead. Dr. Trajkovic, this virtual space is now yours.
Thank you very much. Good afternoon, everybody. Thank you very much for inviting me to give a talk. It is really a pleasure and honor. So I will be talking about some projects that I have been working on for the last decade. And they're all dealing with machine learning for detecting internet traffic anomalies. I come from Communication Networks Laboratory. It's my lab at Fraser University in a Burnaby campus. And so on a sunny day, the campus looks like this. And today is one of the sunny days. SFU celebrated 50 years in 2015, so we are a young university. We do have a couple of campuses, but I reside at the Burnaby campus. This is a roadmap of my talk. I would like to introduce the topic. Why is it important to look at the traffic? And people have been looking at the traffic of the communication networks for a long time. But it's very exciting time to do this now because internet carries such a variety of traffic in terms of voice and video, images, all sorts of interactions. So even my talk today, it's actually carried using packets that actually traverse the internet. I'll talk about data collection because it's very important if you are interested in designing and defining and the models, traffic models, in evaluating performance of various protocols and algorithms. And I usually rely on deployed networks. And so the data collection is a rather important part of actually a project where you want to do anything with machine learning. We'll talk about feature selection. Features are very important aspects of the data, and especially combination of features and selection of features in terms of the importance greatly affect the performance of the algorithm. And then I'll talk about machine learning models that we created. We looked at deep learning networks, broad learning system, which is a rather novel architecture where we do not go deep into the network. We actually make the network very broad. And then something that's also of our interest are gradient boosting decision trees, because one of the goals is actually to have fast algorithms that don't take too much time to train the model, in hope that some of these systems can be actually implemented in real time. So when there is an onset of anomaly, virus, ransomware attacks, or anything that can interrupt the internet, that the administrators can actually take the network element down before it propagates through the network. I'll provide the experimental procedure that we use. Actually, we build the tools, so we are very much software oriented. And so I'm going to introduce a cyber defense. It's a tool that we built in order to enable the comparison of the algorithms. And I'll talk also about the performance, just to give you some feel about what is the level of accuracy, F-score, sensitivity, recall, or overall confusion matrix when we look at it that can be achieved with these algorithms. And usually I provide a conclusion and provide references for people who are interested in actually pursuing this kind of research. So traffic measurements are really basic for characteristics of network traffic and developing traffic models. They are used to evaluate performance of protocols and applications. And this is why we have so many applications on the internet today, because it's very easy to actually introduce them. But to evaluate the performance, it's always good to have realistic traffic models. Traffic analysis provides information about network's usage. That's very much of interest to internet service providers. It also helps understand how users behave. From the research point of view, traffic analysis also provides information. How did internet topology evolve over the last 2 or 3 decades? And the topic of my talk is really that traffic analysis enables classification of traffic and detection of network anomalies. Prediction is more difficult, but the models are also important for traffic predictions because it's very important to assess future network capacity requirements and to deploy network elements in order to maintain the quality of service that the customers expect. And also the traffic prediction is important to plan future network developments and employment of network elements. There were 2 major findings 2 decades ago that are related to understanding the traffic and the internet. So this is a pictorial view to show you that the influence of timescales, because what it was found out is that the traffic that we see today in the internet is fractal in nature. And that's very much different from the old-fashioned models that we used in order to model voice traffic that was carried over communication networks of the past. So I hope you know a little bit about the fractals, but this is a very interesting way of actually looking at the traffic. This is a genuine MPEG traffic trace. On the left-hand side, we have one time scale, which is 4 frames, and it depending on the coding schemes. In this case, these 4 frames represent 160 milliseconds. And so every bar actually indicates how many bits do I have per frame. And you can see peaks and valleys, right? So we are looking at 500 frames. The traffic is bursty. We have a lot of peaks and valleys. And let's change the time scale. Instead of 4 frames, let's look at 16 frames. So basically, we are zooming up. And one can see now that on the vertical axis, of course, the number of bits per unit is going to change. It's going to increase from 300,000 to 1 million. But qualitatively, the picture remains the same. So the yellow part on the left-hand side is just the little piece of yellow in the middle graph because we zoomed out. But the message is that peaks and valleys remain. We do this once again by looking at 64 frames or 2,560 milliseconds. That's a time unit. We are now looking at a much larger period of time, longer period of time. The number of bits per time unit increased. Now we talk about 5 million because, of course, we are adding all these bits per time unit. The green part in the middle graph, it's actually a little piece of green in the right-hand side, but one would argue that actually peaks and valleys remains. And that was a very interesting idea how to actually, in an illustrative way, show that the traffic is fractal in nature. And it really comes from a seminal paper by Walter Willinger and his team. At that time, they were at Bell Communications Research, and I happened to work there before joining academia. And so the paper was published in February 94, and in 95, he received the Bennett Award, which was at that time the best paper award in all IEEE transactions. So it was really seminal departure from Poisson models that were very suitable to model traffic that was carried over communication networks of the past and the internet traffic that we see today that carries voice and video and images and all those social media interactions. Of course, we can use a Poisson model in order to capture the traffic on a certain scale. And so what we see on this slide, it's actually on the left-hand side, the same model, right? Same traffic captured with Poisson model. But if one changes the time scale and uses the same model, you can see that at the end, we basically get a white noise. So even though you can still create Poisson models on a certain time scale, one cannot use those models on different time scales. So this talks about the traffic that we see today and its fractal nature. Now, something else was also found at the end of 90s, and this is the introduction of what we call scale-free networks. It turns out that over the 5 decades, people have used random graphs in order to capture connectivity in engineering systems, biological systems, chemical reactions. But when people look at the internet topology on a certain level, granular level, it turns out that that topology has very specific properties. And so in 1999, and later on in a journal paper in 2003, Brother Falutzas actually came up with a model for internet topology on what we call autonomous system level. So autonomous system is actually a unit. It's a campus network, company network that has one administrative domain. So we are able to look at this internet on autonomous system level and find out that this is how the connectivity looks like. So that's very much different from random networks. And so it has been accepted that now if you would like to model internet topology as a static graph, we talk about what we call scale-free graphs. Scale-free graphs means the degree of the node, it's not bound. So as the networks grow, the nodes that are rich are going to get richer, and the nodes that are isolated are going to remain isolated. So this view is from CAIDA, it's Organization for Internet Data Analysis. It's affiliated with University of California in San Diego, and it's just one view that captures over 500,000 nodes and over 600,000 links, and it shows a very interesting graph. So these are two major findings in terms of understanding the traffic and also the connectivity internet. So now the data collection, usually it's very nice to have data that are available to research community. So luckily we do have two collection sites. One is in Europe, one is in North America, but actually they do have collection sites all over the world. And we looked at the anomalies that were introduced by Internet Border Gateway Protocol, or BGP. BGP is a de facto industry routing protocol. And so we look from historical perspective, the computer worms and viruses, they happen in 2001 and 2003. We really wanted to see like, how is it possible that the internet was taken down for such a prolonged period of time during that time. We also looked at some electrical failures, not necessarily malicious. For example, Moscow blackout happened in May of 2005. And it turns out that the trafo station south of Moscow in a place called Shigano had electrical failure, and that actually propagated and could be seen in the data that was collected by Riper route views. Pakistan power outage was also of interest because as internet evolves, it's always interesting to look at the data that's more current. And more recently, we were very much interested in ransomware attacks. One called WannaCrypt happened in 2017, and more recently, the company called Vestrock was attacked in January of 2021. So there are really three very different phenomena: worms and viruses, electrical failures, and more recently, ransomware attacks. There are also a variety of other anomalies, such as Internet Protocol prefix hijacks, sometimes misconfigurations. They are not necessarily malicious because sometimes it's a human error in configuring the routers. And as I mentioned, we have two collection sites. The data are available to the research community because doing measurements on your own, it's very expensive, and it's also very difficult to connect your device to the network because of proprietary reasons. When we analyze our data, it's always good to look at the representation, at the view, the graph. So this is a view of the Pakistan power outage in 2021. What we see on the graph on the left-hand side is a collection from the RIPE. Main collection sites are in Europe. Route Views was a project from the University of Oregon. Main collection sites were in North America. And so what we are seeing is a reported anomaly that happened in January of 2021. And how do we know? We look at the white papers, we look at the email messages, sometimes we read newspapers in order to identify when was it reported that the power outage took place. We always look at days before and the days after. So what you see in the middle is these are red dots. That means these are anomaly points. We would classify it as a class 1. And the blue points are regular points because one would like to have balanced data sets so that the data set that we analyze has both regular data and anomalous data. This is very much a simplification. And later on, I'm going to mention that we do label refinements because not everything within a reported window of anomaly is actually anomaly. People have also used the internet as regular customers. So it's always good to look at these graphs to sort of see what are we classifying, because identification of anomalies is nothing else but a classification method. So I would like to classify point whether it's anomaly or not. So we talk about two-way classification or binary classification. Of course, one can engage in multiple classifications, identifying what exactly is the anomaly, but that's also sometimes very difficult, and the algorithms, of course, don't have the same performance. This is a Vestrock ransomware attack, just to show you that it's a very different phenomena from power outages. So what we see, it's a date in January of 2021, when the Vestrock ransomware attack was reported. We look at some features, such as number of implicit withdrawals. This is one of the features of Border Gateway Protocol, and the number of duplicate announcements. Of course, we look at the different combination in order to have a better representation and the graph. Everything inside the red window is anomaly. These are longer events, and unfortunately, ransomware attacks are becoming very common. That means a malicious user is going to encrypt the data of a company, university, or hospital, and it's going to demand the ransom in return for returning the data to the rightful owner. And these periods of time are longer, and that's going to also affect the performance of the algorithms. But one can see that whether we look at RIPE or route views, it's a similar phenomenon. Different collection sites, but we are collecting the data from the same network. Something from a historical point of view, just to give you some feel about what are the data sets we talk about. Very often these data sets are very manageable, rather small. I'm showing here the table for Slammer, Nimda, and Code Red. These were major attacks on the internet 2 decades ago. We have 3 collections from RIPE and only 1 from route views because they started the collection in 2003, while RIPE collected the data in 2001. Code Red happened in July of 2001, Nimda in September of 2001, and Slamas happened in January of 2003. And so you can see that the data set is very manageable. These are smaller data sets. We talk about, in terms of duration, the minutes for regular data points, anomaly data points. Of course, we divide the data set into training and test. So these are just gory details about the numbers that we use. We usually publish this because we would like people to reproduce our results. So in order to have this reproducibility of research results, one has to be very precise about what kind of data we're analyzing, what is a start and end date. So just to give you a feel that this is very much doable on a simple CPU, but we also use a GPU in order to do analysis. This is RIPE and route views for the Moscow blackout and Pakistan outage data. Very manageable, small data sets. Okay. Now, when we look at ransomware attacks, it's a longer duration. And as I mentioned, we are looking at 2 of them, Vanacrypt and Vestrock ransomware attacks that happened in 2017 and 2021. Now, we also try to visualize some of the features. So what we see on this side is a view of the slammer. It happened in 2003. It took internet down for a prolonged period of time. So for example, yahoo.com was down, NewYorkTimes.com was down for more than 24 hours. It took internet community very much by surprise because at that time, these kind of attacks were not very common. So in the meantime, people have found methods and tools in order to prevent these kind of attacks. But the malicious users are very creative in terms of finding other ways to take the internet down. So this, what we see on the left-hand side, is number of BGP announcements. Basically, the routers are announcing what are the good paths and good routes in order to reach, per packet to reach the destination. So we see a number of BGP announcements. On the top, we see data from RIPE. On the bottom is route views. One can see that during a time when the virus was announced, very visible increase in terms of volume. And this is usually indication that something is happening. Usually these are denial of service attacks. That means a malicious user is going to attack a server with bogus request in order to take a server down. And this is exactly how it happened 2 decades ago, that these major sites were taken down by having this denial of service attacks. So distributed denial of service attack, when you have a master attacker and slave PCs that are actually taken in order to do attacks on the servers. So one can see the increased volume, and as I mentioned, you can see it on the left-hand side on the top for RIPE and on the bottom for route views, and the increased volume usually means that something bad is happening. Moscow blackout lasted only 4 hours, but during those 4 hours when the blackout was reported, one can see also the increased activity. So it was very interesting to see how algorithms are going to perform for such a data set. This is a Pakistan power outage, another view, right? So we talk about the number of announced prefixes, number of implicit withdrawals versus the date. And as I mentioned, we always try to have a balanced data set. We look at the windows of anomaly, and also we look at the data before and data after. Vanacrypt, different view, number of BGP announcements and announced prefixes versus date, and what the red window indicates the reported time during which the ransomware lasted. Vestrock in 2021, same idea. Feature selection is very important, and in the old days, there were separate algorithms to extract features because we would like to extract the most relevant features from the original data set in hope to improve classification performance. There was a variety of selection algorithms, and usually they're used in order to reduce redundant features. And how is it done? It's done by ranking and identifying the most relevant features. So, for example, Fisher, MRMR, MyBase, odds ratio, they were all algorithms that we use in order to figure out what are important features, because there is a point of diminishing return. You can use all the features, but you have to introduce to use a lot of memory, a lot of CPU time, a lot of time. So there is a point where you sort of decide, well, I'm going to work only with features that are most relevant. Not only that are most relevant, but I'm also going to watch for the combination of features, because that's also going to affect the performance of the algorithms. Very recently, we used decision trees and extremely randomized trees in order to do feature selection. And the reason why we are very much interested in feature selection is because we will show that selecting right features or most important features is going to affect the performance of the algorithms. A little bit of math, but just to show you that we use Gini importance to compute feature scoring in a given data set. So this is a mathematical representation. There are tools readily available in order to do importance. And so there are methods and tools to actually calculate the importance of the features so that one can make a decision which features are important in order to do that. We also use dimension reduction. This is the only time that we use actually unsupervised learning. Everything else I'm going to talk about today is supervised learning. That means the data have to be labeled, and that usually takes time. But for dimension reduction, we use the unsupervised learning. We transform the original data into lower dimension in hope that that lower dimensional data preserves the characteristics of the original data. For this, we use autoencoders. These are unsupervised neural networks, and they are there in order to learn representation from a given data set. We combine deep autoencoders with various deep learning networks, such as LSTM and GRU. LSTM stands for long short-term memory, GRU for gated recurrent unit, and so we experimented with using this for dimension reduction. Autoencoders, this is a high-level view, and sort of to remind us that our input is actually a time series. These are not images. So we are looking for algorithms that actually can handle time series. So this is a high-level view of autoencoder. We have input, we have encoder, we have a code, we have a classification algorithm, then the decoder and the out. On the right-hand side, you can see the effect of the autoencoder. In the left column, we see the original data, right? This is a slammer when we sort of focused on the time, on the period when the volume was increased. And then when we go to the reconstructing data, using the lower dimension, one can see that that volume is also preserved. And one can see also that on the left-hand side and the right-hand side, a lot of similarities, because even when we do dimension reduction, we are supposed to preserve the main characteristics of the data. BGP data slammer, 2003 again, what are we going to try to achieve? We are trying to classify the points. So it's very important to figure out what's the combination of the features in order to have a separation of two clusters. Red, which is anomaly, which we call class 1, and blue, which is regular class, it's a class 0. And we actually experimented with 3D figures and views in order to show that in this case, for slammer, the separation is quite visible. So we expect that the algorithms are going to do much better, because basically we are trying to do a two-way classification. Things are a little bit more complicated when we look at the power outages. So we can see that separation is not that visible. Separation between red and blue, right? On the left-hand side is a write, on the right-hand side is route use collection. And so as expected, the algorithms are not going to do as well. The internet has also changed in the meantime. So 2 decades ago, worms and viruses were rarity. Also, people have used internet in a different way. So it's not surprising that actually the classification was much easier when we've dealt with viruses and worms that don't happen very often. Even worse, right? So you can look here, right? Very difficult separation. And for ransomware is all over the place. And that's a sort of indication that we should not expect that algorithms are going to do as well. So that's why we are searching for the best one. That's also a view from the Vestrock. And let's move on to machine learning models. First, we are going to experiment with a variety of deep learning networks. And so we looked at coarse and supervised machine learning algorithms until now. We are very interested in semi-supervised and unsupervised. But in the past, we only used supervised. That means that somebody has to put the labels, and that's very time-consuming. We looked at support vector machine as a classical approach to doing classification, convolutional neural networks, recurrent neural networks, such as long short-term memory, gated recurrent unit, and their bidirectional version. We also looked at something quite novel. It's a broad learning system, or BLS, with a variety of its extensions. It was introduced at the end of 2017, and now quite a few groups are actually looking at BLS because it's a different approach. It's not a deep network, it's a broad learning system. And I'm going to show you the architecture indicating that there are other ways to actually compose the neural networks, and instead of going deep, you can actually go broad. Of interest was also gradient boosting decision trees family of algorithms, or GBDT, because they are also very fast. And one reason why we looked at BLS and GBDT was because they are fast algorithms, in hope that the speed of training the model it's of relevance if you want to do something in real time. 3 families, 3 algorithms within GBDT, XGBoost, LightGBM, and CADBoost, so we're going to compare them. This is how CNN network looks like on a high view. This is a high-level structure using one-dimensional data. These are the data that we are dealing with. This is an input layer. Then we have feature maps. We have max polling, the usual routine, the usual track. Then we feature maps, and then at the end we have flattening. So we have these fully connected layers. We play with a number of layers. And at the end, we have the output layer, in our case, with 2 nodes. Because we are only interested to classify whether the network, the point is anomalous or not. And as I mentioned, this is a 2-way classification. One can actually extend this to have multiple level classification, when one can identify whether it's a power outage, whether it's a ransomware, or what kind of virus it is. And we also experimented with that. Our deep learning network doesn't have to be that deep. As I mentioned, this is all very doable on an ordinary PC, CPU, GPU, or we also have a supercomputer at SFU that we use for certain tasks when we create the model. So this is example when we use 37 recurrent neural networks, 80 fully connected nodes in the first layer, 32 in the second, 16, right? And so that's how it looks like. So we have input layer, we have recurrent neural networks. And so in addition to RNNs, we also have these fully connected layers, and then finally the output layer. So that's a high-level view of what the structure of the network is. Long short-term memory, or LSTM, was introduced quite a while ago, but it became very popular with the last 10, 15 years. This is a repeating module of the LSTM neural network. One can see the nodes, the functions that are there, and so then the LSTM cells are stacked. And I only cited the more recent reference from 2017, which is a nice source of information. For those of you who are mathematically inclined, actually, all of this has a very nice mathematical representation. Sometimes we forget about that because we have so many ready tools and libraries to use. So these are mathematical representation for various gates, such as forget gate and the input gate and the output gate in LSTM cell. And this is sometimes very interesting to mathematicians and people who do control theory, because you have all sorts of questions that we actually did not answer. For example, what is the region of convergence of these algorithms? What is the region when I should choose my parameters in hope that we are going to find a fixed point? Do these mappings also have fixed points? So these are still open questions, and I understand in a control systems community, they are very much of interest. So sometimes we forget there is a mathematical description of all of this, what we represent usually with nice graphs, or we use from Python libraries readily available to the research community. So this is output of the input gate, cell states, output of the LSTM cell, and just a reminder there is a math behind. Gated recurrent unit, or GRU, is a simpler, very simpler version of LSTM, equally powerful, simplified, so that means it takes a little bit less time to train the model, and it's a similar idea, just the cell is simplified, it doesn't have as many nodes, and you can see we only have the reset gate and update gate. Again, we do have sigmoid function that we use, we have input, previous output because the cells are stuck, weighted matrices, and bias vectors. And of course, we are always interested in the output of the cell. So simplified version, but equally good in terms of performance. Broad learning system is something relatively new to the community. We were very much interested in broad learning system because we wanted to see how it does. What is the performance when we deal with time series data? BLS was first applied to images, and it comes from Philip Chen and his group. I think they're now in South China University of Technology in China. He moved from Macau. And so he came up with this idea that we actually don't have to go deep. We can actually have our network to be broad. So you can see the broad structure of the network. You can see the input X, these are the data, output Y, dynamically updated weights. And something very interesting, we have two sets of nodes, map features nodes and enhancement nodes. Something interesting is that this structure has incremental flavor. If we would like to increase the performance, we can add map nodes, we can add additional enhancement nodes. Not only that, we can also add new data without actually retraining the network. And that's a nice property because the weights are dynamically updated. So now we're going to, this is original BLS, just to tell you that we actually can construct these matrices. There is a math behind, but something very interesting. What makes these networks fast? If we do not use the backpropagation, we use what we call Moore-Penrose pseudo-inverse of the matrix, and that makes the algorithm very fast. So there is a very nice mathematical theory behind, and all of this can be modified to actually add this incremental flavor, to add map features, to add enhancement nodes, and to add also input nodes. And so this is very much of interest. Let me just mention when we have to analyze large data sets, because you can train the network with a portion of a data, and then you can add additional data without retraining the network. So it's very suitable for large data sets. There are also extensions for BLS, various flavors. One is, for example, to add the radial basis function. And so one can also add a depth. We don't call it deep layer, we don't call them cascades. One can cascade the map features by keeping the enhancement nodes flat, and that can increase the performance of the algorithm, and it's adding some depth. And of course, there is a mathematical representation. One can do this with enhancement nodes, or one can do this for both. So this is how in image processing, for example, they increase the performance of BLS by adding the depth through the cascades. And even if one does cascades, you can still do the incremental part. Now, our contribution recently was to actually add the features. And this is why I was talking about importance of features, right? So we added the feature selection algorithm in order to select the features that we find that important. There is some domain knowledge there because we know my group also works with protocols. And so with a filter in front for feature selection algorithm, we were actually able to increase the performance, to improve the performance of BLS. And so this F in the title actually indicates that we have features and we can vary these features. So we call the algorithm VFBLS. One can actually do this with cascades. One can add a cascade, similar idea, just the filter in front to select good features. And one can add incremental learning, of course, that's always something we use. Gradient boosting decision trees were also very interesting to us. They are fast algorithms. They are family of gradient boosting machines. These are boosting algorithms. They use functional gradient descent to minimize the loss function. So it's really optimization method. And a variant of GBM is what we call gradient boosting decision trees. Three algorithms that we look, XGBoost, LightGBM, and CADBoost. So these are the main properties of the algorithms. For example, XGBoost adds the L2 norm regularization toward overfitting, and it uses second-order Taylor series approximation as its objective function, to approximate objective function, because these are really optimization methods. LightGBM, very much of interest to us, very fast, and then CADBoost that has a nice property that you can actually use immediately categorical features. In other cases, if you have categorical features, you have to convert them into numerical. In case of CADBoost, you doesn't have to do that. So that's a nice property of CADBoost. For experimental procedures, as I mentioned, we build software tools. So this we call cyber defense. This was a work of my PhD student who in the meantime graduated. And this is a tool for detecting network anomalies. We posted it on GitHub. And so this is a high-level architecture. On the left-hand side, we have a data container that can be custom data sets or ripe and route views that I was very much mentioned, but one can actually deal with other data sets as we did. There are two paths. Top is a real-time, bottom is offline. In real-time, we have to do real-time data retrieval. So this has a web-based interface. And then we have to do feature extraction and then move to data processing. In offline mode, we do data download offline. We do feature extraction. As I mentioned, we also try some label refinement. This is the idea that within a reported period of anomaly, actually there are regular points. And we wanted to see whether some of the algorithms we use, such as k-means, can help actually extract the regular points. Then we do data partition. In most engineering endeavors, people use 80% of data for training and 20% for tests. In our case, it turns out that with our data, using 60% of anomalies for training and 40% of anomalies for tests produce the best results. Then we do data processing. Of course, there is a lot of work to actually put data in a form that's suitable for applying algorithms. We do feature selection. We do dimensional reduction, and of course, normalization. And then we can actually take also the models from a library that we call model oceans. These are pre-trained models before we move to application of machine learning algorithms. Variety of those. The most time-consuming task is actually selecting hyperparameters. And for that task, we use a supercomputer. We call it Cyber at Simon Fraser University. And so that usually takes a lot of time. We do insist that we still do tenfold cross-validation for the parameters, even though we have a large data sets. And then we create a model. And once we have a model, we can do classification. This is a more detailed view of a part of the tool that deals only with BGP. We call it BGP card. And I'm pointing just to show you that we have a lot of libraries that are available to research community to do all of this. And some of the tools we actually brought in, such as C# tool, in order to extract the data, put it in matrices in a forms that we can apply the algorithm. And many of these libraries are very readily available to the research community. You don't have to scratch, not to do anything from scratch. Now, as I mentioned, our data are time series data. We do a tenfold cross-validation. This is how we create the folds. And as I mentioned, this is the most time-consuming task in order to get the best parameters. What do we look at the performance? We look at training time because of the nature of the problem that we are trying to solve. And of course, the usual accuracy, F-score, precision, sensitivity, and sometimes we look at the entire confusion matrix. So performance evaluation, just to give you a feel about, in general, feel about what these algorithms do, and to sort of justify the conclusions that we have. As I mentioned, selecting first number of features, it's a choice. You might want to introduce all features, right? But you might also to think about which features are important. So this is an interesting graph that I thought I'll show you for another data set. It comes from a Canadian Institute for Cybersecurity. It's, I believe, in New Brunswick. They do have data. They're not necessarily BGP data. They're data from TCP flows. But we thought it's interesting because the graph shows some interesting phenomena. So we look at the accuracy and F-score as performance on the left-hand side. We look at the training time on the right-hand side, and we look at the number of selected features. Two algorithms are featured, BLS and incremental BLS, blue and red. And one can see that when we increase the number of features to 78, there is a point of diminishing return in terms of performance. Of course, in terms of timing, more features means more time. And you notice that, for example, incremental BLS did very well, much better than the regular BLS, because the training time is much shorter. Now, this is a performance of the models. And I'm going to only show you Westrock ransomware because it was more recent and more interesting to us. But in our publications, we also cover all sorts of other anomalies. This is a convolutional neural network. We experimented with no refinement with the window and refinement with k-means and isolation forest. Notice the training time. We are talking about 20 seconds approximately. And accuracy, F-score, precision, and sensitivity varies. But just to get your feel, we can maybe get accuracy of up to 57%, F-score 72. These are the best results that I put in red. This is about CNN. Now we also experimented with RNNs, recurrent neural networks. And the little number on the bottom shows how many hidden layers we had. We selected the best performance. The training time, much better than compared to CNN. Over there, we talk about 20 seconds. Now we talk about sometimes even less than 15 seconds. Accuracy, F-score, precision, sensitivity do vary, but more or less the ballpark is the same. We compare GRU and LSTM. And as I mentioned, GRU has comparable performance very often, and it's relatively faster because it's a simple cell. And we also looked at bidirectional version. Of course, it takes longer time because you have to make a pass twice, back and forth, but it increases the performance. So bidirectional GRU, for example, with various hidden units, did much better compared to the one directional or simple GRU. BLS, as I mentioned, very short training time. And that was our interest to actually evaluate this algorithm. We are talking about order of magnitude training time. There is no back propagation, right? And so the algorithm is very suitable for tasks that you have to do something fast. We looked at no refinement data. Isolation forest and k-means did more or less the same. So I'm going to show you only results for isolation forest. Order of magnitude faster training of the model and relatively good performance, at least comparable. Now we also talk about incremental version, right? So incremental version does better. And as I mentioned, if you have a large data set, it's a very suitable model because you don't have to retrain it. If you add features with a filter beforehand, better performance, a little bit more training time because one has to use the filter. One can add the cascades and improve the performance. So this is our flavor of improving the BLS by adding the variable features and adding the cascades. And so we actually experimented with all of this. We put this out there in order for people to be able to reproduce the results. Now, in terms of GBDT, let's see, XGBoost, very good training time. We talk about 540 milliseconds, accuracy, F-score, precision, sensitivity. Not everything is 90%. So I'm trying to show that this algorithm, this is what they can do for the data that we have. Light GPM, right? So that's the fastest algorithm. It took 50 milliseconds to train the model compared to 20 seconds that we started with. and comparable accuracy, F-score, precision, and sensitivity. CAD-boost the same, a little bit slower, but it can handle categorical features. So in conclusion, so we did a variety of things. I introduced the traffic, I introduced the internet topology just for us to understand where the data comes from, because we always worry about the system where we collect the data from. We looked at a variety of algorithms, convolutional neural networks, recurrent neural networks, including the LSTM, GRU, and their bidirectional versions. We also varied the number of hidden layers. We looked at the BLS models. We looked at BLS model with and without incremental learning, and some flavors of BLS, such as BLS with radial basis functions. We also used the cascades of map features and enhancement nodes in order to increase the performance and to add some depth. And we also looked at the feature selection filter in front, and we used integrated extra trees. One can use any feature selection algorithm in order to do the filtering before, and in many cases that improve the performance. And we also got very interested in GBDT because these algorithms were introduced approximately at the same time as BLS, and they actually show that in some cases they're faster than BLS and much faster than the other algorithms, especially when we talk about line GBM. I usually provide the references. They should tell you that we're actually building on other people's work. First, the data sources. We look at the RIPE Network Collection Center. As I mentioned, many sites are in Europe, even though they do have locations in other parts of the world. University of Oregon route use project started in 2003, and they are still collecting the data. So data are readily available to the research community. Of course, you have to do a lot of work to download the data, to clean the data, to put the data in a certain format. We also look at other data sets that I didn't report today. NSL-KDD is like a benchmark, very much used in image processing community, but they also have some data for the network flows. And more recently, University of New Brunswick actually got the original data set. It's come from KDD 99, but they cleaned it up and they made it available. The Canadian Institute for Cybersecurity has a lab. They have a collection of synthetic data. So unlike everything else that I talk about, which comes from deployed networks, the Canadian Institute for Cybersecurity has a test lab. And they do have a huge number of a variety of denial of service attacks, very large data sets, but synthetic. And it turns out that when you applied algorithms to this synthetic data, the algorithms did extremely well. Because the conjecture is that there is no human in the process. So from deployed data sets, you have customers, you have humans coming and going, doing all sorts of things on the internet in a very controlled environment. When you have synthetic data, this shows as a very good performance of machine learning algorithms, 99, 98%. CAIDA is a Center for Applied Internet Data Analysis, and I give them a credit for actually the graphs that I showed you at the beginning, because they have an interesting project called Walrus Project, and they have these beautiful images showing that internet is a rather complex system. The nodes are, even in a static view, show that it's what we call scale-free network. And you can imagine if we add the dynamics on nodes, how complex the system is. Many tools out there. We talk about Python, Pandas, PyTorch. Zebra DAM parser is available on RIPE and RouteViews because the data are collected in binary form. So you really need a conversion to ASCII. We have our own tool for conversion to ASCII. And very recently, we actually created a tool when you don't have to convert to ASCII and use all that memory. You can actually convert the data from binary directly to the form that can be used by machine learning. The clean data that we use in our studies are uploaded to IEEE data port for the research community to use, both from BGP, they are all BGP data, from RIPE and from RouteViews. Philip Chen's group that introduced BLS, they have their own websites, and the software tools are available on their site also. So there are many tools readily available out there. I usually put references for people who are interested in intrusion detection. These are references very much related to intrusion detection in communication networks. And so they're easy to read. We talk about communication lectures. We talk about survey tutorials. RAND Corporation also had a very nice submission, publication, and also ACM computing surveys, if you are interested in the topic. Deep learning, many tools for deep learning, many sources. I only put some major ones for your interest. BLS, as I mentioned, Philip Chen and his group, these are the first journal papers that appeared in January of 2018 and then in 2019. And of course, the GBDT algorithms, XGBoost, LightGBM, and CutBoost. We also have our own publications. They're all readily available on the webpage. You don't need a password. We have a journal publication in 2023 that actually dealt with synthetic data, showed the performance. And in July of 2021, the recent one is in a magazine that came last year. We had 2 book chapters, I hope easy to read. The first one is about data collection. At that time, gory details about what are the data we are collecting, how do we classify the data. The second one is about algorithms. But you notice that this was already published a while back, excuse me. So it doesn't include the more recent algorithms. We also do a lot of conference publications. We have one that's coming in May of this year because we did evaluate a variety of traffic sources, a variety of algorithms, a variety of anomalies. We also looked at other networks such as ATCO State Network, and I didn't really talk about that, but there is a variety of other algorithms to use. So these are some of our conference publications. And I want to leave you with this view of the internet. It's also from Qaeda, to show you how interesting the internet is in terms of source of data and source of also of unresolved questions about understanding such a complex system as the internet, both in terms of traffic, in terms of internet connectivity. And so that's one view also from Qaeda, to show you that there is so much more to do in terms of understanding internet as a communication network, also as a tool that we use now to communicate in our daily life. So that's all what I have to say. So thank you very much.
Thank you so much, Dr. Trajkovic. With that, it is now time to begin our Q&A session. So just as a reminder to our online audience that you can use the question icon to the right of your screen to ask questions. This is a moderated format. So once questions are published, you'll be able to see them and upvote them. And I will do my best to select a broad range of questions. So just with that, I will jump in and see what questions we have from our audience. Our first question for you, Ljiljana, comes from our audience member, Patrick. Patrick asks, how costly or disruptive would a false positive predicting an attack when there isn't one be? And how expensive is it to put countermeasures in place when an attack occurs?
Yes, that's an excellent question. I didn't talk about confusion matrix, and actually, depending on the problem you're trying to solve, sometimes false positives and false negatives are very much of importance. So I only show the sensitivity, the F-score, accuracy, but we also look at the precision matrix. So false positives are serious issues in some systems because you don't want the alarms to go on. But equally, in some other applications, false negatives are also very dangerous. This kind of algorithms can also create the matrix when you can look at these false positives and false negatives. And I know in some engineering systems, false positives are quite serious matter. In terms of communication networks, false positive would probably mean that you take a router down, and so that it doesn't affect the rest of the network, because that means it's indicating that there is an anomaly even though there is not. So in internet, I think it's doable, and it's not such a major issue as, for example, in some other cases where false positive would mean taking the entire floor of the operation down. So in case of communication networks, because we have all these network elements that are manageable, and sometimes in software-defined networks, we don't even have a hardware. We actually can do this through software. So it's a relatively doable compared to other systems, and false positive would be a major issue.
Thank you. Our next question comes in from our audience member, Robert. Robert asked, you said that a 60-40 data training split gave you the best results. How did you decide that?
Because we did experiments. We started at the beginning with 80-20, because that's usually engineering, approach, and everybody else is doing it. And we thought, okay, let's experiment. So most of the people would take 80% of data for training and 20% for test. In our case, we take 60% of anomalies, not entire data, but anomalies for training, and 40% of anomalies for tests. So we changed this. How did we decide? We did experiments. And so it turns out for our data that we analyzed and our algorithms, 60-40 in terms of anomalies was the best separation. But you have to do experiments. There is really no math that you can do in order to predict that.
Amazing. Thank you. Just looking to see if we have any more questions. I might give the audience a minute to submit any more.
So just to fill the void, originally when we started this, the hope is that we would have online system. But it turns out that building online system was rather difficult, right? So we are now trying to build the online system where at the onset of anomaly, the system administrator can take the router down immediately, right? And so in our cyber defense tool, we actually have this part where you can actually do the collection online. And so just to justify why we were experimenting with so many algorithms, we were looking for fast algorithms so that you can train the model fast, and at the onset of anomaly, you can actually take the network element out. Usually it's an router that has to be taken out. So
thank you. Wait and see. It doesn't appear we have any. Oh, here we go. We have another one. Another question from our audience. Have there been step changes in attack behavior? Would your model be able to adapt to them, or would it require retraining?
That was the hope, that the model would adapt. But originally, when we start looking at this, we looked at worms and viruses from 2000, and people said, well, things have changed. Why do we look from historical reasons for this? So now we only mention it for historical reasons, because in the meantime, things have changed, right? And so people have found out the ways in order to predict, to prevent all these viruses and worms. And this is why we do updates, we do patches. It's an open question if something new comes, whether these algorithms will be able to adapt. Our experience is that algorithms perform very differently for viruses and power outages and ransomware attacks. And ransomware attacks, the performance was relatively low because it's a different phenomena. It's a different system. So even within one kind of phenomena and anomaly such as ransomware, the algorithms, it's difficult for them to learn, right? But that's the goal. And it's also goal to move into unsupervised learning, because you have to get away from this requirement that you need somebody such a resident expert in order to do the labeling of data. And in our case, our approach was very simple at the beginning. Everything reported is anomaly. And of course, life is more complex than that. During that period of anomaly, people do use internet in a regular way. So it's open question, how can these algorithms adapt? We only look at certain phenomena, but of course, at the same time, there are other phenomena that are happening, right? So we are really not trying to identify what, we are just trying to identify whether it's anomaly or not. We have a two-way classification. But that's always a question, right? How generative the model is, how capable the model is to learn something that was not trained on.
Thank you. And another question from our audience, is the structure of internet behavior different in different regions or countries?
Very good question, of course. When we talk about traffic in general and phenomena in internet, we always see this. First, I'm going to go on the side a little bit, seasonal behavior. That means people use the network differently during working days, during holidays, right? During different seasons. So that seasonal aspect of traffic and happenings in the internet is very much present. And the same is for geographical data. At this moment, we are looking at the data from the places of conflict. And we are finding out that actually one can see huge changes between before the wars and attacks and after the wars and attacks. So at this moment, we are looking at this. So yes, geographic location very much affects what's happening. In cases when we talk about viruses and worms, we try to collect the data from the place that's very close to the epicenter of the anomaly. For example, if we knew that something was happening in North America, such as, for example, a ransomware attack on Vestrock, we would download the data from the collection sites in North America. Right? Of course, yes, geographical location does affect. It also affects what's happening in the world. And so, as I'm saying, we are sort of looking at data now in the times of conflict. How are the data reflecting what's happening in the world?
Thank you. Just check and see if there are any other questions coming in from our audience.
And maybe one message to give is there are many tools out there readily available, but it's very important to understand where the data come from, what is engineering system behind. And this is why we always look at the protocols and the network, because it's not just a stream of numbers. One has to understand where the data come from in order to actually do the labeling properly and to understand the phenomena. Because my group is not a statistician, we don't do just statistics, right? I come from the School of Engineering Science and from the Communication Networks Lab, and so we started doing this maybe a decade ago, but we do bring in the understanding of the protocols and the traffic and the internet connectivity in order to better design the algorithms and choose the parameters in order to have the better performance. Because it's just not trial and error, and this is what I usually tell my students. There is a mathematical theory behind, right? So all these tools that are available are there to make it easier for us to actually do the evaluation, but that doesn't mean we need to understand, right, what these algorithms do, right? It's not a trial and error. And so that's why I was saying it's important to actually find the region of convergence of these algorithms. Do they have fixed points, right? And so these are difficult questions. But trial and error is not usually a best approach to actually solve the problem at hand. Right? Some understanding of the system where the data come from are very important.
We did get another question come in. The question asks, or says, I can picture how a DDoS attack causes visible network anomalies, but what's going on during a ransomware attack to affect the network on a large scale?
Ransomware are very different from DDoS attacks, and this is why it's very difficult to actually tune the algorithms to do reasonable performance. It affects the company. because the operation of the company was taken down for a prolonged period of time. So Westrock is a company in North America. I think they have locations all over the world. And so basically the operation of the company stopped. And so you can see this on the data, right? Because during the period of ransomware attacks, everything in the company was frozen, right? Usually people don't talk about it, but it was reported, right? So it affects the operations. So that means no internet connectivity, the operation of the company had to cease. And that affects like the communication between the company and the rest of the world. And I'm mentioning Westrock because we looked at this because it was in January of 2021, so relatively recently at the time when we start looking at this. There is no communication, right? Everything is frozen. And unfortunately, ransomware attacks are something that's happening to universities, to hospitals. But it's a different approach. It's an encoding system. You encode the data and you give the data back only when the ransom is paid. I hope I answered your question.
Yeah, definitely. No, I think you did. We have another question coming in, and the question asks, how difficult is it for a human to tell regular traffic from anomalies?
Well, when there is, when your system goes down, you can tell. So, for example, to take this Slama and Code Red and IMDA, because it was such a major attack on the internet. Basically, the server goes down. So New York Times was down for more than 24 hours. Yahoo.com was down for a prolonged period of time. So this is how it's said. But that's the outcome, right? This is when it happens. During the time when the attack is happening, people are actually observing the traffic, right? So the system administrators look. Sometimes there is a deep inspection of the packet. So there are many ways of looking at there is something unusual happening, like a large number of requests for the server to provide the data. And so that's usually a volume of the data is indication that something is happening, something bad is happening. So usually it's the volume. If you have an increased number of requests for downloading data from a server, unusual, right? That's indication to look and see whether you can stop it.
Very interesting. We have another question from our audience member, Janelle. Janelle asks, is it getting more difficult to get data sets for research with the recent LLMs making headlines, showing how much monetary value there is to data?
Mm-hmm. Well, yes. You see, in the past, when telephone companies collected the data from telephone networks, that was not available to the research community. Like universities didn't really have courses to teach students about the traffic. Traffic was collected all the time, but usually people were trained when they get a job with Bell Labs or AT&T or whatever the company was. They would train the new employees on the data that they have. The data was not shared. Were not shared with the universities. So in 60s and 70s, when the Professor Kleiner from UCLA introduced his queuing theory books, suddenly it became interesting to look at the Poisson model as a model for voice traffic because it was very tractable and you can apply queuing theory ideas in order to do that. So now that we then cannot really use Poisson models, we cannot use the classical queuing theory, people are relying on collecting data from the network. So in 1995, 93, 4, at Belcore, the group actually collected the data from the backbone that connected the Belcore to the rest of the world, right? And so it was now never made public, right? But it was used by the group to actually find out that the traffic is fractal. Now we have Ripe and Routeviews. They are collecting the data as we speak, and that's available to the research community. And that's very important, right? So how feasible is to get the data from Facebook, Twitter? I think some people do manage. They are not publicly available, but it would be very nice, to get some data because we cannot talk about performance of machine learning without the data. And I'm talking about good quality data. So it was always difficult to get data that are not done by Ripe Use or CIC initiative or the NSL-KDD from University of California. Yeah, it's very difficult to get data. We had a project with BCNet. BCNet is a provider for internet services to universities and high-end education and hospitals in British Columbia. And we actually had a grant and we bought a device. It was very expensive. And we had collaboration with BCNet to connect the device to the network. We had two devices to collect 1 gigabits per second data from 1 gigabits per second link and 10 gigabits per second link, right? But it was all with the understanding that we will only share the clean data. The clean data meant we can only share a mapped IP address, so one cannot actually identify who was the user sending. The only thing we preserve is the number of bits or bytes and the time of arrival, right? So that was one of the projects that we involved, and we really couldn't share the data at the end. So yes, it is complicated, it's difficult. Many companies are not going to release the data because once you have the data, you know everything about how they operate. You know how they charge the customers, you know what is the quality of service, are they really delivering what they promise? And so that's why the companies are very possessive about the data. But luckily for the research community, we do have some data available. And I understand some people also through collaborative efforts have the data from social networks, which would be very interesting. But difficult to get the data. And I'm mentioning the project where we actually had the answer grant. We had a device that we bought. We connected it. That was around 2011, 2012. And so we have some data from BCNet. We didn't really see any anomalies. Everything was regular, but it was a nice set of data to sort of compare with something that we actually measured. Very difficult to get a permission. In order to get a permission from a company to connect anything to the network, it's a difficult process, and usually it's an issue of trust. So if you have a long-term collaboration, right, if we trust each other, then they will let you collect and they will let you use the data. We also have a data from ECOM network. ECOM network is a preparedness network in Vancouver. They actually provide the security and the network services during the Olympic Games, but we had to sign a non-disclosure agreement and we could not share the data. So this was a very interesting data, not from internet, from a network used by police, fire departments, all technology, push-to-talk devices that they used at the scene of the crime where the police would come, right? And so it was very interesting analysis of traffic, not necessarily anomalies, it was traffic analysis. But we couldn't share the data, but we got the right to publish. But the data, we never got the right to post the data. So getting data is very difficult. Usually, if you have a long-term collaboration, we had it with the BCNet, then it's an issue of trust. It's also we would never, if we collect the data, it's always only the packet, only the header. Inside the header, you can find out the source, the destination, the protocol, the versions of the protocol. But IP addresses have to be mapped. And in order to get a permission to actually use the data from BCNet, we had to go all the way to Ottawa to get the permission. It took us like 1 year. It's a very sensitive issue because it's a privacy issue, right? So usually for the sake of analysis, we would keep the number of bytes that are collected and the inter-arrival times, right? It's a statistical process, but never the IP addresses of the source and destination and never the payload. Because the payload carries a privacy information. So the privacy issue is very, very important. So there are many tools that people use in order to sanitize the data. It means to clean the data in such a way you can make it publicly available without revealing the source of the packet, the destination of the packet, some proprietary information, and never the payload. So, but we are talking about traffic collection, right? But difficult to get data.
Thank you for sharing that. I'm going to see if there are any other questions coming in. We have a bit more time. Might give it a minute and see. And
And of course, there are other algorithms that I didn't mention, such as we looked at echo-state networks, for example. So that was very promising, right? But I didn't mention it. So there are a variety of algorithms out there. And many people are now concentrating more on actually understanding the data, looking at the data properties. I know some people are interested, for example, in data coming from BMI and BCI networks, brain-machine interface and brain computing interface. So I'm looking at data from there in order to understand certain anomalies, because we worked on this for a decade or so. So I think we are moving in some other things in the meantime. But the data from such networks, like a brain network, very important, and you can actually do it without invasive procedures. There are electrodes that you can actually collect the brain waves. And there is a large research community that actually does that. We call it brain-machine interface, a brain-computer interface research. And so they're also looking at applying machine learning algorithms to data coming from those kind of networks, brain network. And especially if you do it in a non-invasive way, right? So we did the experiments with our students, right? And you can look at the image and you can actually see the pattern compared to when you listen to the music. Very interesting area where people are applying machine learning algorithms in order to identify the patterns. So there is a famous experiment, and they have a monkey, and the monkey gets a banana if by just thinking can move the circle to fit within a certain other circle. And it's possible, we can train it, right? And there is no joystick, there is nothing, right? Just electrodes connected. So it's a famous experiment. They actually, and it's really very, very, has very much a humanitarian aspect, because you can help people who have disabilities in order to function, right? To move the wheelchairs, to actually control the robot who is going to help them. So it's a very nice field, very interesting field. But you also work with data and machine learning algorithms in order to help the humanity have a better life.
Amazing. Yeah, very interesting. Thank you for sharing that. Perfect. Okay, I'm just taking a look, and we don't have any more questions. So I think with that, I might start to wrap up the webinar. Ljiljana, thank you again so much for your time and for sharing your remarks and answering some of our questions that came through. It's such an interesting talk and a very relevant subject for all of us. And I also want to thank all of my ATCO colleagues who have helped put this event together. And of course, everyone who's joined us today online. We very much appreciate your interest and invite you to join us at our next speaker series. Our next one that's upcoming is on March 15th with Dr. Nathaniel Trask. And I'd also like to remind you that this lecture, along with all previous speaker series lectures, are shared on ATCO's YouTube channel. So with that, I want to encourage everyone to stay safe and enjoy the rest of your day. And thank you. And thank you again, Ljiljana, for your time.
Thank you very much for having me.